Hello and welcome to our podcast, where we dive into the latest and greatest in AI-driven math reasoning. I'm your host, and today we're discussing an exciting new approach called rStar-Math. Let's meet our experts.
Hi everyone, super thrilled to be here. I've been researching math reasoning and language models for a while, and rStar-Math, well, it's quite the game changer.
Absolutely. I'm pumped to chat about how they've made these smaller models, or SLMs, rival big guys like OpenAI o1 in math tasks. Seriously, that's no small feat.
And hey everybody, can't wait to share how these new techniques actually translate into the business world. After all, it's not just about passing math benchmarks, right?
Exactly. We're hearing that rStar-Math uses what they call a self-evolved deep thinking process. Expert 1, could you walk us through the fundamentals?
Sure, so rStar-Math basically combines two big ideas. First, they do code-augmented chain-of-thought data synthesis. That means they don't just spit out the math steps in plain text. They generate Python code that checks correctness on each step, ensuring fewer logical mistakes.
Right. So instead of the model just hoping it got the math right, it actually runs the code to verify each step. That reminds me of those geometry problems in high school. If only I'd had a code execution tool back then.
Me too. I would have saved hours on proofs. But the second piece is that rStar-Math uses a process preference model, the PPM, which is like a built-in critic for each step, right?
Precisely. That PPM looks at each partial solution and says, is this step good or not? Then it assigns a score. It's kind of like a personal trainer that encourages you at every step of your workout, as opposed to waiting till the end to say you did good or bad.
I agree with you, Expert 1, but I have a slightly different perspective. I think the biggest advantage is how these SLMs can bootstrap themselves. They do multiple rounds of generating data, then retrain on that data, then generate more, each round getting better. It's like they're learning from themselves over time.
So it's a continuous feedback loop, if you will. Now the business angle. Imagine you're an e-commerce platform with complex sales data. Maybe you need to project inventory turnover or solve advanced financial formulas. You can feed problems into rStar-Math, and it systematically breaks them down, verifies each step, and corrects itself if needed.
This System 2 style reasoning they describe, it's reminiscent of how humans solve tough problems, right? We do it step by step, we check our logic, we reconsider. Expert 1, where does the self-reflection piece come in?
Well, rStar-Math has shown some surprising emergent behavior. The SLM stops mid-route, sees something is off, and picks an alternative path. It's basically going, wait, that approach might be a dead end, let's restart. That's the kind of meta-reasoning that bigger models have, but we're seeing it in a 7 billion parameter model.
Now that's wild. I remember reading that it solved an Olympiad-level question by discarding the first approach and spontaneously using a new method. So it's not just mechanical repetition.
Speaking of Olympiad-level math, let's think about a real-world case. Suppose a finance team needs to do complex derivatives pricing, like advanced math. Historically, you'd hire a quant with a PhD or rely on massive supercomputers. With rStar-Math, a smaller-scale solution can achieve a near-expert-level approach step by step, double-checking with code.
That's huge from a cost standpoint, right? You no longer need a 175 billion parameter model that breaks the bank in GPU hours. A 7B or even smaller model might suffice.
Exactly. It democratizes advanced math capabilities. But watch out, because there's a fair amount of pre-processing. You need those multiple MCTS rollouts, and each step must verify with the code. Still, if it's feasible to do that offline, you can train an efficient model.
And the synergy is that these steps are curated, like the system only keeps good paths. In a normal single inference approach, you might see a weird step 9 times out of 10. Now it's like a teacher saying, nope, that's incorrect at every turn.
I've got a question for you both. How do we see this method scaling to domains outside of math? For instance, code generation or chemistry.
Potentially, if you can define a verification procedure. For code, you run unit tests. For chemistry, maybe you simulate reactions. You do the same step-by-step approach. The model tries a step, it's verified, so you keep it, otherwise you discard it.
I agree with you, Expert One, but I have a slightly different perspective. The challenge is that in math, the correctness is unambiguous. In something like marketing analytics or creative writing, correctness is more subjective, so the verification step is trickier.
That's fair. Still, it's an exciting possibility. I'm imagining an MCTS approach for generating marketing slogans. That tagline is weak. Next.
How that might be a comedic scenario, but who knows? Now, a question. Do you see any disadvantages or limitations?
Well, yeah, it's definitely more computationally expensive at test time. If you want 64 trajectories, you're going to generate a lot of tokens. You need to weigh that against using one big pass with a huge model. But if you can tolerate the repeated expansions, the final accuracy is quite impressive.
And also the reliance on correct code references. If your code libraries don't handle a specific advanced function, or if the model hallucinates some weird library import, you have to manage that.
True. Also, in business, we must ensure data privacy. So if we're running these rollouts in a secure environment, that's one consideration. But it's still more feasible than calling, an external black box service 1,000 times.
So how might a mid-sized company use rStar-Math practically? Any short success story or hypothetical scenario?
Sure. Let's say a logistics firm wants to solve dynamic routing problems. They feed in constraints, times, costs, and the SLM runs these step-by-step expansions. It checks each route with a small subroutine like, is this route feasible under time constraints? And picks the best solution after verifying. That's a huge business value add.
Exactly. Fewer delivery delays, better resource allocation. They might even incorporate real-time traffic data if they embed the logic in code. The MCTS approach ensures they systematically explore multiple routes before finalizing the best one.
With a bit of excitement. And let's not forget the self-improvement angle. The model can learn from solutions that worked, refine its steps, and next time produce even more accurate or optimal routes. So it's iterative improvement.
I love that. Now, we're nearing the end of our show, so let's do a quick recap. Smaller models plus MCTS with code verification plus a process preference model that, basically ranks each step. End result, near frontier level math reasoning. Did I get that right?
That's spot on. And I'd say from a purely technical vantage, it's proof that we don't always have to chase bigger model sizes. System 2 reasoning is letting us get more out of smaller systems.
And from a business standpoint, you can see real ROI in domains that rely on advanced math, finance, logistics, engineering. rStar-Math has practically brought the big model capabilities to mid-sized players.
Indeed. I can't wait to see more expansions of this concept. Maybe soon we'll have specialized smaller models for everything from supply chain optimization to cryptography.
Let's mark the date. This was a fun and enlightening talk. Thank you all for sharing your perspectives, both the technical and the real-world angles. And thanks for giving me a good laugh about marketing slogans, too.
It was a blast. Thank you.
Same here. Thanks for hosting us.
Really enjoyed it. I hope everyone can see how game-changing rStar-Math can be.
That's all for now. Keep exploring, keep innovating, and we'll see you next time. Take care.